Hello, I'm Daniele Sensi, and I'm going to present you this work we did on the analysis of the impact of network performance and network performance variability on the performance and scalability of applications running on HPC in the cloud systems. So different providers nowadays provide different solutions for building small HPC clusters in the cloud. And in this work, we're going to analyze some of the major providers. So we analyze 4 cloud providers. And we are also going to compare those with some on-premise HPC systems. And the reason why we focus on the network is that if we observe the characteristics of CPUs that are present on both cloud and on-premise HPC systems, we can see that actually there is not so much difference. There are not so many differences between those. In all those cases, they deploy either Intel or AMD CPUs with different characteristics due to different generations of those CPUs, but overall they are just more or less the same technology. And if we are going to look at the GPUs, we can have a similar picture. So what really changes between cloud HPC systems and on-premise HPC systems is the network. And if we're just going to look at the bandwidth, we can see that in principle they also all have a quite similar bandwidth, around 100 to 200 gigabit per second. But actually, if we see to the technology that it is deployed, we can observe many differences. In terms of the network, in on-premise HPC systems, we usually have non-blocking full bandwidth networks, whereas on the cloud, this might not always be the case. And there are cases where blocking networks are deployed. And the same goes for the transport protocol. So now, although there is some kind of convergence towards RDMA, and even though in different flavors, most cloud providers deploy RDMA, there are some differences in the technology and in the protocol, and this is actually what makes the difference when running an application on the cloud instead of on an on-premise system. And we are going to analyze those differences in practice by running benchmarks and simulation to see and to understand whether those HPC in the cloud system can be a viable alternative to on-premise systems. So in this work, we are going to divide this presentation basically in 2 main parts. So in the first part, we are going to compare the network performance of cloud HPC versus on-premise HPC systems. So we're going to run some benchmarks and analyze the network performance. So in this presentation, for time reason, I'm just going to show a few of the results we have. You can find more in the paper with more detailed benchmarking. So after analyzing the performance, we're going to analyze through simulations the impact of network noise on cloud HPC and on-premise HPC systems, and its impact at scale. So with cloud noise, with network noise, we mean any kind of variability in the performance induced by the network. So this is usually happening because of congestion or because of different reasons. So let's start with the first part. So in this part, we're going to analyze basic network performance metrics for both HPC in the cloud and on-premise HPC systems. And the first thing we're going to analyze is bandwidth and network bandwidth and network latency. So to do so, what we do is it's a classical ping pong micro benchmark where we have 2 servers exchanging a message back and forth, and we're going to analyze and to measure the bandwidth and the latency. So on this plot, we have on the x-axis the message size. So how large is the message which is sent back and forth between the source and the destination, and on the y-axis we have the bandwidth measured in gigabit per second. And we have one line for each of the systems we are analyzing. And we can see that most on-premise HPC systems, as well as some cloud providers, they can all reach around 100 gigabit per second. That is what we would expect according to the numbers I showed at the beginning. So for PitStaint, we are around 75 gigabit per second. This is just because the network interface card is 85 gigabit per second NIC. But the surprising thing here is mostly about GCP and AWS that with 16 megabyte messages, they can still reach 100 gigabit per second network bandwidth. And even to get this 70 gigabit per second network bandwidth, we had to play some tricks, which are described more in detail in the paper. So we can already see some differences here between all those different systems. To dive further in, we are also going to show what happens to the message latency, and we're going to show this in this inner plot here, where we basically zoom in this first part of the plot, and where instead of showing the bandwidth, we show half of the round trip time. So how much time does it take from the moment where when we transmit the first byte of the message from the source to the time when the last byte of the message is received at the destination. And again, we can observe here some differences. So basically all the system except for GCP and AWS exhibit a round trip time of around half a round trip time of around 1.5 microsecond, more or less. For GCP and AWS instead, we observe up to an order of magnitude more, an order of magnitude higher latency. And again, this is due to technological reasons and to the network protocols that are deployed. Another important thing to analyze is whether it's convenient or not to rely on an HPC instance versus a normal instance. And the reason for that is that, of course, there is a matter of cost involved. So HPC instances are more expensive than normal instances. So we would like to analyze whether there is some difference in network performance between those. And what we can observe here is that in all those cases, we actually get an improved bandwidth. So moving from normal instances to the more expensive HPC instances, of course, you will get a higher bandwidth. But what we don't get is necessarily a better latency. So again, for AWS and GCP, what we observe here is that even if we move to an HPC instance, we do not necessarily decrease the latency. We can observe here from this plot here where we have the normal instances versus the HPC ones. So we get a small improvement, but not that much. And the same also happens for GCP. While for Azure and Oracle, actually, we can see a significant drop. So the latency drops from around 30 microsecond to 1.5. So if you have a latency bounded large scale distributed applications, it might be not always worth considering spending more money for running this on HPC instances. So on the paper, again, you will find more details and a more detailed discussion on differences and similarities between these providers in terms of network performance. But now I'm going to focus instead of network noise. So, and for network noise, we mean any kind of performance variability that is induced by the network. Usually this is due to network congestion. And for measuring noise, again, we run this ping pong benchmark for 1 hour. And every time that we perform a ping pong, we record the bandwidth we observed for that message. So as you can imagine, there are, in 1 hour, we collect hundreds of thousands of samples. So what we're going to show here is just the top 1% samples with the smallest bandwidth. So we are going to show basically here all those cases where we all those cases where we observe an unusual low bandwidth. And so we have again on the x-axis the time, so this is like 60 minutes. And on the y-axis, we show the normalized bandwidth between 0 and 1. So normalized compared to the maximum bandwidth that we have, that we observe. So if we have a point at, for example, in this case at 0.4, it means that in this case we observed, instead of 100 gigabits per second for Oracle, we observed 40 gigabits per second. Now, we can observe a few things. So we can observe that both AWS and GCP are characterized by high bandwidth noise. So it seems that congestion affects more severely those systems. And another interesting effect that we observe is that on Oracle, we have these periodic bandwidth drops that last for quite a while. So you can see that these are all points clustered in time. So these are all consecutive samples. And in some extreme cases, we observe some bandwidth drops that go down to 2.23 gigabits per second. So quite severe bandwidth degradation. So an important thing to say is that here the two servers or the two virtual machines are allocated on the same rack. So this is intra-rack traffic. We executed the same test also by allocating the two nodes on two different tracks, and we observed quite some similar results, even though usually the systems become more noisy. And for example, we can observe here for the green data points that when the two nodes are on two different tracks, we observe a lot of these very low bandwidth samples. So in general, what we can observe from this first experiment is that cloud systems are more affected by bandwidth noise than on-premise systems. And in the paper, you can also find some more results about also what happens to the latency, so variability in the latency, and also about operating system noise, which is basically performance variability induced by other processes or the operating system itself running on the server. Now, the issue with noise is more evident when we run applications at scale. So when instead of running an application on a few nodes, we start running it on tens or hundreds of nodes, and then at that point, noise might have, this is a well-known result, noise might have a significant impact. And what we want to do here is to analyze specifically what is the impact of the network noise in the cloud. So whether this is going to have a larger impact compared to what happens on traditional HPC systems. And to understand what do we mean about noise at scale, let's analyze this example here. So we have on the y-axis the time, and we have 4 hosts, 4 servers denoted from H0 to H3. And they perform some computation and then send some data to some other node. And they do this iteratively. So this is quite common, for example, in I don't know, deep learning training, but in many distributed workloads in general. So what happens here now is that let's assume that, for example, H3 is sending some data to H1, and this message gets delayed because of congestion. Now, what can happen at the next step, which is not shown here, is that since this message is delayed, the H1 will start its compute phase later, which means that will send its message later. Now, what happens in general is all these delays might accumulate. So in turn, the message sent by H1 might be delayed again, and so on and so forth. Or they might cancel out each other. So it's not easy to understand just with pen and paper what's going to happen, how noise will propagate in the system. And then we need to run experiments to observe what will happen because of noise. And the way we do this, of course, running large-scale experiments on the cloud, it's not really feasible mostly because of cost reasons. but also because of quota limitation. So all the experiments we executed, we just executed them with a normal account on each of those providers, and those accounts, when they are created, they have a lot of limitations in terms of how many virtual machines you can create and so on and so forth. So running a test on hundreds or thousands of virtual machines on the cloud was not really an option. So what we did instead is we took the network performance measurements I showed before, and then we use and also the network noise measurements, and we use those to simulate the performance at scale. So we take measurements from point-to-point communications, we feed them into a simulator, and we're going to simulate what happens when we increase the number of nodes. And the first thing we do is to validate the simulator. So you can find details, you can find more details about the simulation infrastructure in the paper. But what we did is that, so the maximum number of nodes we could run on any of these cloud providers was 16 nodes. So we allocated 16 nodes on each of those providers, we ran some workload, and then we simulated that workload in our simulator by considering only point-to-point measurements. And then we compare them. So we compare the runtime of the simulated workload with the runtime of the actual workload on 16 nodes. And as we can see here, we were able to simulate the performance quite closely. So we have a good simulation accuracy. Starting from that, we are going to run simulation on more nodes. So in this example specifically, I'm going to show what happens for a 512 megabyte ring collective simulation. So ring collective is typically used in a lot of machine learning training workloads. So it's quite representative of common type of traffic. So we will have different subplots. In each of these subplots, we have on the x-axis the number of nodes, in this case from 4 nodes to 1,000 nodes. And on the y-axis, we have the runtime. So pay attention, because here the y-axis doesn't start from 0, because otherwise it will be not possible to observe, to read the plot properly. So we have the blue line, which is indicating the case where there is no noise. So we are simulating a noiseless system where everything is predictable and there are no delays, further delays induced by network congestion and so on. And then we have a first box that shows what happens with operating system noise, which I didn't discuss in this presentation, but basically we can see that it doesn't add any performance degradation. And then we have other two boxes that show what happens when we add network noise and what happens when we add both type of noise. And we can see here that network noise increases the runtime quite a lot. So here we run the experiment several times. So we show here with a box plot all the different samples. But we can observe here that, for example, for 64 nodes, if we don't have any noise in the network, the runtime is around 200 milliseconds. But as soon as we add noise, using the noise we measured on the actual system, we can have up to 400 millisecond runtime. And we did this for all the systems, and we got quite similar results. So the take-home message here is that bandwidth noise can increase the runtime by 50%, even when running at small scale, like on 4 nodes. So if we what's known here, for example, we can see that even with 4 nodes, we get quite some big performance degradation. So the last experiment I'm going to show is an experiment where we execute a dummy application which performs a 8K by 8K matrix multiplication followed by some more reduce. So basically we interleave communication and computation. This is because in the previous slide, I just showed an example where each node was only communicating. But we want to observe what's going on both in terms of performance and cost when actually an application does computation interleaved with communication. So in this specific application, in the specific application, each server was spending around 20% of time in communication. Okay, so it's like 20% of time communication, 80% of time computation. And we want to observe what's the impact of network noise on the economic cost of running such an application. And we show in these plots, again, on the x-axis, we have the number of nodes, and on the y-axis, we show the cost increase. So how many more dollars do I have to spend because of network noise? So what's the economic cost of network noise? So what's the impact on performance and thus on cost induced by network congestion and by the fact that some messages are delayed and the application gets lower? And we can observe here that even on a relatively small node count, like with 16 or 64 nodes, we can already observe a 20% cost increase for an application that spends only 20% of time in communication. And this is true both on the cloud and on HPC system. So the take-home message again is that network noise also impacts the monetary cost, and this is true even for applications that are not dominated by communication. So to conclude, in this work, we analyzed the network performance of cloud HPC and on-premise HPC systems by running several micro benchmarks. I just show some of those here in this presentation. We then analyze the impact of bandwidth noise, both at small scale using real measurements on those systems, and then by extrapolating these measurements and simulating what would happen at a larger scale. And what we observe is that network noise has a large impact on both the performance and the monetary cost of applications running on the cloud. And you can find both the data and the code we used for performing these experiments on GitHub. And with this, I conclude my talk.